Now that we've discussed exponential functions and their properties, we can take a look at finding the inverse of the exponential function. And you see before you some comments I've made about reviewing inverse functions. Number one, you have to have a one-to-one function, excuse me, in order for your function to have an inverse, which means you have to pass the vertical line test to be a function and the horizontal line test to be one-to-one. You find the inverse by swapping x and y and solving again for y. The domain of the function and the range of the inverse are equivalent, as are the range of the function and the domain of the inverse, because you're swapping the ordered pairs. And the swapping ordered pairs results in graphical symmetry about the line y equals x. So looking at the figure before us, we have a graph, in my screen it's in pink, of y equals a to the x. Note that it is 1-to-1. So what you'll do to find the inverse is y equals f of x. 2, we're going to swap x and y. And this produces a rule that is the rule for the inverse, which is x equals a to the y. Now, what we really want to do is solve for y. And we run into a little bit of a roadblock because the y we wish to solve for itself is in the exponent. So we've gone from one exponential statement to something else that looks exponential. This happens a good bit in mathematics where we create a symbol to indicate what we're trying to identify. So we know what we mean. We mean x equals a to the y. What we're going to do is use the symbol y equals logarithm base a of x to mean x equals a to the y. Okay, so this is the definition of the logarithm. So the graph in blue is the graph of the inverse of the exponential function that's in pink, and this means a to the y equals x. Okay, so the symbol that we call a logarithmic symbol is again representing the inverse of the exponential function. And so notice the properties are, go along with it are present. The domain of the exponential function is all reals. Its range is 0 to infinity because it has a horizontal asymptote, y equals 0. When you swap x and y, the domain of its inverse is going to be the original function's range, and the range of the inverse is the original function's domain. So the logarithmic function with base a has domain 0 to infinity and range all real numbers. And you can see the symmetry about the line y equals x. Now to give you a real specific glance here at the relationships between the two. For example, you see before you a pink graph that is the exponential function with base 3, so y equals 3 to the x. We see an ordered pair, 2, 9, that when we swap x and y would produce an ordered pair of 9, 2 on the graph of the inverse. So again, symbolically, we're notating the inverse as y equals log base 3 of x. But what this symbol means is 3 to what power produces the value x. So let me show you the analogy here. If I write over in this world, in the exponential world, that 9 is 3 squared, okay? In the corresponding logarithmic world, I would write the power 2 is log base 3 of the value 9, and I mean the same thing. So notice again, this means 3 squared equals 9, which is exactly what we were saying up here. Okay, so we go back and forth between what we call exponential form and logarithmic form using this definition. But it's important that you keep it simple. The logarithmic function of base a of a variable x is simply the inverse of the exponential function whose base is also a to the power of x.